All right, as you're settling in, take a look at this Le Chatelier's principle question. You have a system, we've let it come to equilibrium. It's A plus B goes to 2C. Notice those phases. And then we do 4 different things. Okay, imagine this as a Karman test question where after each one of those changes, there's a drop-down menu. And you could pick shift left, shift right, or no change for each one of those 4 disturbances. How is the system going to respond to those changes? Okay, so pull your notes up from the end of Tuesday. Turn to someone next to you, see if you guys are pointing in the same direction. All right, drop-down choices are 1, 2, and 3. We have a secret way of removing C, okay? So we take some C out and just C. Are you picking 1, 2, or 3? Good. 2. If I pull products out of the reaction, okay, so what we're saying here is that Q equals K to begin with. We can view this through the lens of our reaction quotient. We are beginning at equilibrium, okay, so Q equals K. The system is balanced, it's happy where it is. All right, we pull out some C, okay, now it's not at equilibrium, okay, and in fact, if we write out our Q and technically K expressions here, I'm gonna have, I didn't specify, we'll call it pressures. So when I lower the amount of C, right, because I pulled it out, now Q is going to be less than K. So the system responds by making more product. Okay, so this is a shift right. How about the addition of B? I'm going to put some more of my solid in there. 1, 2, or 3. Good. You are not tempted to answering 1, okay? B does not show up in my expression because it's a solid. I just need to know that it's there, okay? So I've told you that the system has come to equilibrium. There must be some B in there to have a dynamic equilibrium. Adding more of it is not going to change K. Q is K throughout that whole of B. So I'm picking 3 for this one. All right, an increase in temperature, what's that going to do for us? Is that going to shift left or shift right? Or no change? You can pick no change. Good. The key to this is to recognize the delta H is negative, so it's an exothermic process. All right, that means that we should view heat or temperature as a product. All right, so in this sense, we are adding product. So we're going to force the system back towards the reactants. So that's a shift left. Okay, that one is a little bit different because, of course, K is actually changing, but K changes in a way that we're going to make more reactants. So we'll still talk about it as a shift left. Okay, and then lastly, an increase in volume. 1, 2, or 3. Good. Okay, I'm seeing a little bit of a mix, which makes sense. This is a little bit tricky. I selected 2. You might stop and be like, hey, it should be 3. I'm not changing the number of moles on the left and right, and we can't change the equilibrium unless there's a change in moles, but it's moles in the gas phase. Okay, so there's only 1 mole in the gas phase on the left side, and there's 2 on the right side. So an increase in volume is going to favor the side that has more moles. Okay, an increase in volume will drop our pressure. Our system responds by trying to get back to that pressure, and it can do that by making more moles, by making more C. So that is also a shift right. Okay, this is a good style of question, or representative of what you might see on the exam. Okay, we'll have like some reaction. We're going to mess with it in a bunch of different ways, and we ask you to tell us how it changes. All right? So that was chapter 15. And now we are like officially into our chapter 16 business. Okay, we ended talking about Bronsted-Lowry reaction, or acids and bases. Here we're looking at a Bronsted-Lowry acid-base reaction in the gas phase. We've broadened it so we don't have to talk about aqueous solutions anymore. All we need for a Bronsted-Lowry acid is something that can donate a proton. And a Bronsted-Lowry base is something that accepts a proton. Remember, proton is just H+. It's a hydrogen that has lost its electron, and most hydrogens are just one electron and one proton, so that leaves us with that single proton. Okay, so when you're looking, one of our first questions to you on an exam will be to say, hey, can you identify the acid or base in this reaction? And so we're looking across the reaction arrow. Who gained a proton, who lost one? Okay, so from here to here, I see that Cl went from being HCl to Cl minus. It must have given away or donated that proton. So here's my acid. And once I identify the acid, if this is a valid acid-base reaction, the other thing must be our base. It had to accept that proton. And you double check and say, yes, it did. NH3 became NH4+. Okay? So this is like the most prominent definition, the Bronsted-Lowry definition that we're going to use in 16 and 17. Okay. So we ended on this slide, all right, where I said some things, some substances, some chemical species can act as both an acid and a base, right? They have a proton to give away, and they also have lone pairs so that they could take a proton. So whether they act as an acid or base will depend on who they are partnered with. Okay, so these things that can do both are called amphiprotic substances. So can act as an acid or base. Which one the substance decides to do depends on what else is in the mixture. Okay, so H2O has protons to give away, and oxygen also has two lone pairs or two non-bonding electrons that could be used to take a proton. Okay? In this first reaction, it's reacting with HCl, which I think are all comfortable with seeing as I feel like my volume is inappropriately loud today. Okay, HCl is an acid, and so it will give away that proton. Water takes it. So water in this case acts as a base because it's paired with an acid, right? But if I pair water with a base, so NH3, hopefully over the next lectures you're going to see that and become comfortable with seeing NH3 as a base, NH3 is more likely to take the proton from water. So in this case, since I have partnered water with a base, it behaves as the acid because it's giving away the proton and our base is accepting it. So I want you to, in the next slide, identify, so we have another amphiprotic substance, so H2S. I have two different reactions. Which one represents H2S functioning as a base? Okay. All right, so are you picking one or two? Good. Okay, Bronsted-Lowry base. That means it accepts a proton. So on the other side of these reaction arrows, we better see H3S+. Okay, so here it is accepting another proton, and it's pulling it from what's acetic acid here. So here's our acid, here's the base. Okay, and this top one, we've partnered it with a base. Okay, so something similar to ammonia, that NH3, this is methylamine. That would be our base, which forces H2S to act as an acid. Okay, because here it's given away its proton. So donated, and here it's accepted. All right. Now, we have one, oh, sorry, go ahead. It donated an H+, and so it became HS-. The H+ has been given to the base, so the base picked it up. So this is a good point. When you are doing these acid-base reactions, you're going to wind up charging some of your species, and make sure you have a charge balance. So if you have a neutral reaction to begin with, you better have a neutral reaction at the end. So notice in both cases, I started with neutral species, and I have a plus and a minus on both sides. So I have a charge balance. I haven't gained or lost protons or electrons. That is good chemistry to remember. All right, we have to expand this one more time. So it wasn't good enough to have two other definitions of acids and bases. We expand it one more time and say Lewis acids and bases. Okay, so this is a broadened definition. So this really is just a generic definition of acids and bases. And we can start from our Bronsted-Lowry. Okay, to accept a proton, if you are a base, a Bronsted-Lowry base, you accepted a proton. To do that, you must have had a lone pair. Okay, so you must have had a pair of non-bonding electrons. So let's look at, we would have hopefully seen this reaction as a Bronsted-Lowry reaction. What we're seeing is, to expand it, to say we're not even going to talk about protons anymore and the transfer of protons, we're going to say the base used its extra pair of non-bonding electrons to take that proton. These electrons go to whatever's left over from my acid, and we wind up with BH plus and OH minus. All right, so a Lewis base donates an electron pair. Okay, and a Bronsted-Lowry base is a Lewis base. Okay, this is broadened, but not all Lewis bases are Bronsted-Lowry bases, so it doesn't go the other direction. We'll draw a Venn diagram. Okay. On the flip side, if we are looking at an acid to donate a proton, so again, we're starting with our Bronsted-Lowry definition. If you're going to donate a proton, that means you are keeping the electrons. Okay, so that's what water did up here. Water acted as the acid, and it kept the shared electrons in that OH bond. So it accepted an electron pair. Okay, so Lewis acids accept an electron pair. So now we are really broad. We're just talking about the donation and acceptance of electrons, which is most of chemistry where we are just making new bonds. Okay, so we're just moving around electron pairs. All right, so let's dig into Lewis bases first. All right, so we have our definition, an electron pair donor. Okay, and I made the point that this NH3, when it acts as a Bronsted-Lowry base, is using its extra electron pair to pick up that H+. So that's how it accepts the proton, is that it has those electrons to make a new bond. Okay, and now we're saying, but it's not necessary to have an H+ or protons or OH-. Okay, this is now really broad. Okay, so this is also NH3 acting as a Lewis base. It uses NH3, the lone pair on the nitrogen, makes a bond or donates those electrons to the boron in BF3. Okay, so this is acting as a Lewis base because it's donating its electrons. And now this does not look like acid-base chemistry in the way that we typically think about it. This is very broad. We're just looking at the transfer of electrons, okay? So to be a Lewis base, you better have a non-bonding pair, okay? If you can donate it, you need a lone pair of electrons or non-bonding pair. Using those interchangeably. Okay, so it should be, another way of saying is that Lewis bases should be electron rich. Okay. On the flip side, our Lewis acids, okay, they of course, actually let me draw my little Venn diagram here. So we have Bronsted-Lowry bases, okay, those are the things that accept protons. Okay, if you are a Bronsted-Lowry base, you are by definition also a Lewis acid base. Okay, so I'm trying to draw a Venn diagram here where all of our Bronsted-Lowry bases are nested inside the Lewis bases. So if you're Bronsted-Lowry, you have to be a Lewis base. But here, ammonia is not acting as a Bronsted-Lowry base, but I would call it a Lewis base. Okay. The same is going to be true for our acids. All right, so it's like, we're not, I'll point out to you at the end of introducing these Lewis acids and bases, how you might see this called out in an exam. Okay. All right, we said Lewis acid is an electron pair acceptor. If the base is donating electrons, somebody better be ready to accept them, right? We can't lose them. So there's 3 types of Lewis acids that are something different than the Bronsted-Lowry acid. So one, we just looked at, it could have an incomplete octet. So BF3, so boron and aluminum are usually going to be these Lewis acids that are just short on electrons, right? If it's going to accept an electron, these should be electron-poor substances. So that boron here only has 6 electrons, right? It's one of our exceptions to the octet rule. It will happily accept those electrons and share them from the NH3. So that's one type of Lewis acid. Another one might be a simple cation. Okay? A cation is certainly short on electron density. It's fully positively charged. So when I see this, I see Fe3+, and I've got these Cn minuses, okay? Those are going to be donating electron density or electrons to Fe3+. So I'd call this my Lewis acid, and this is my Lewis base. Again, notice that we are now not talking about protons whatsoever. This is just very broad chemistry. And then the last type of Lewis acid category that we have that is not one of our Bronsted-Lowry acids is a substance that has multiple bonds. What do I mean by multiple bonds? Like double or triple bonds. Okay, so what we're seeing down here, we have water donating an electron pair to carbon, and the carbon is in carbon dioxide. So it has 2 double bonds. So here's our Lewis base. Water is acting as our Lewis base because it's going to donate electrons. Our carbon in carbon dioxide is accepting them. And the reason it can accept them is because it can easily shift the electrons in one of those double bonds up to our oxygen. Okay, so these arrows are showing us movement of electrons, and then eventually it winds up taking that proton from next door. And we make actually an acid. This is the reaction of why increased CO2 in the atmosphere is making our oceans more acidic. Okay? But that can act, our carbon dioxide can act as a Lewis acid because it has a double bond. All right? So what you might see on an exam, okay, is a very specific question where we'll say, hey, identify the Lewis acid and base in the following reaction. We will specifically call out that we're looking for, by definition, a Lewis acid or a Lewis base. Okay, so you look at this, and now I hope that you could come to a conclusion about who's acting what. somebody should be giving electrons and somebody is going to be accepting them. All right, and so this is following, I would look at this and say, what does that boron have? Again, as soon as I see boron or aluminum, my mind, like the little flag in my head is being waved that says it's an incomplete octet. It's probably a Lewis acid. Okay, so I see boron. So boron makes these 3 bonds with hydrogen, right? And it's certainly short. Okay, so this is going to have to act as a Lewis acid. It cannot act as a Lewis base. There is no lone pair to donate. Okay, it has to be the acceptor. Okay, and then I have this dimethyl sulfide, which probably looks something like this. And sulfur, just like oxygen, is going to carry those 2 lone pairs. Okay, so it has some lone pairs that it can donate. And that's how we're going to make the connection between these 2 and make this new compound over here. So on an exam, you might have some multiple choice questions that say, which one is the Lewis acid? And you say, oh, it was BH3. And then you say, why was it the Lewis acid? Because it accepted electrons. Okay? That might be how we break it out in an exam question. All right, so on your exam, moving forward, in this chapter and the next one, Lewis acids and bases are not our focus. You can feel pretty confident that you're going to see one question on the exam that asks you to identify a Lewis acid and Lewis base, or something of that ilk. Okay? But otherwise, we default to the Bronsted-Lowry definition. We are really going to be focusing on aqueous systems, so where water is our solvent and we're moving some protons around. Okay, so from here on out, unless I say Lewis acid base, I'm really talking about the Bronsted-Lowry definitions. Okay, so again, down here, if I'm going to ask you about Lewis acids and bases, I wouldn't describe BF3 as just an acid. I would describe it as a Lewis acid, okay? Some definitions moving forward in nomenclature. I'm not asking about Lewis acids and bases or these exceptions unless I call it out. Otherwise, I'm thinking about proton transfers. Yes? Okay, you have to know those definitions. We can't get around that. All right, let's move on to conjugate acid-base pairs. This is our next big step. All right, and we've already sort of tackled this. All right, in the forward reaction, HA acts as the acid and water acts as the base, right? We know that because we've given away a proton from HA and water's accepted it, okay? That's in the forward direction. I'm going to take that reaction and I'm going to flip it, okay? I'm just reversing it, all right? And now, if I look at it in this direction, now who's acting as the acid, right? H3O plus would be the thing that donates the proton. So now that is an acid, and A minus is accepting it, and so this would be my base, right? So when we flip it, we realize that once something acts as an acid, if it gave away its proton, it's now in a position where it could accept the proton back. So it has become a base. That's what we call the acid conjugate base pair. Okay, so this is HA is the acid, and I'm going to call A minus its conjugate base. Because now A minus is short a proton, and maybe it wants to take it back. So now it's in a position to act as a base. All right, this is true for every single acid-base reaction. You will always generate the conjugate acid and the conjugate base. All right, so here's an example here of HNO2 acting as an acid. Right, it gives its proton to water, so water's acting as the base. But now on the other side, we've created NO2 minus. If I just put that into solution, I would look at that and say that's a base. Right? It's in a position to take a proton back, okay? To accept a proton, meaning that it's a base. And H3O plus, well, that has an extra proton that it could donate. So that's the conjugate acid. So I want you to be really comfortable identifying conjugate acids and bases, because they're not going to go away for the rest of this chapter. the next 2 chapters. So really make yourself comfy here. So I want you to write down the conjugate base for these 3 species, and then write the conjugate acid for the next 3. Okay, so when I ask for conjugate acids and bases, I am thinking about proton transfer. That's a requirement here, that once I say conjugate base, we are in the Bronsted-Lowry acid base definition. Okay, so we're thinking about protons being moved back and forth. Okay, so turn to someone next to you, write these down. All right, unpack this. Conjugate base, what's the conjugate base of? If I'm asking for the conjugate base of something, then the something I am referring to must have acted as an acid. So it had to have given away a proton. So HClO4, you might recognize that as one of your strong acids. So maybe it feels comfortable to say, oh, when it goes into water, it becomes H plus and ClO4 minus. That is its conjugate base. Okay? Yes? Thumbs up? Okay. pH4 plus. That is going to act as an acid in this question. So I'm looking for the removal of a proton. pH3 would be its conjugate base. And then HCO3 minus would go to CO3 2 minus. Okay? And then down here, what is the conjugate acid? And so that framing of the question tells you that I'm thinking of these things acting as bases. So they must have accepted a proton. And now in theory, they could act as an acid because they have a proton to give away. So HCN minus would pick up a proton and be HCN. That's my conjugate acid. SO4 2 minus picks one up, HSO4 minus. And lastly, I'd have H2CO3. So make sure that as you are adding the proton on, you are also acknowledging the proton carries a charge, so I should be adding a +1. Yeah, Anna. Because when it acts as a base, it is only going to take 1 proton. I could then have it act as a second, like secondarily, do it again, but I'm always going to do it stepwise. Yeah. Yes, because it acted as an acid, so it must have given away or donated a proton. So I got to take a proton away from HCO3 minus. So it becomes CO3 2 minus. Yes, so it was already negative. I took another plus away. It becomes 2 minus. It has an H that it can give away. All right, so this should feel very quick, okay? Stay with me. All right, we've got this down. We're always going to have a conjugate acid base pair, always, all right? Now we need to acknowledge that we have been looking at a bunch of different acids and bases, and they are not all created equal, right? We are going to have a spectrum of strength. Some acids are better at donating protons, right? Some bases are better at accepting them, okay? So we want to define that. A strong acid is something that completely transfers its proton away. And by that I mean 100% of our HA molecules become H plus and A minus. It's not like it partially dissociates and the bond breaks 90%. No, I'm talking about like every single HA becomes H plus and A minus, all right? A weak acid partially dissociates, okay? And that means that a percentage of the molecules give up their H plus. This is where it's like, it's not like, oh, the H is like kind of hanging on. It's either hanging on or not, but we say on average, like 1% dissociates or 50% dissociates, okay? So let's draw this out. If we have a strong acid, that goes into solution, I should only see H plus and A minus. I will never find HA in that solution, okay? Because a strong acid, by definition, completely dissociates. A weak acid, okay? A weak acid, I will wind up seeing a lot of the HA, but I will also see some of it dissociated, right? I have a small percent. We'll say 100% dissociates. Here, you know, let's say 1%. We'll say a small percentage. We won't quantify it yet. Small percentage dissociates. A negligible acid is one that doesn't dissociate at all. So I should have no H plus in here. Okay? So that middle ground, that weak acid, we are going to have an equilibrium, a balance of HA and A minus and H plus. And lucky for you, we just spent a whole chapter talking about equilibrium. So we're headed towards quantifying this dissociation using our equilibrium laws from chapter 15. Something to look forward to. All right, so now we have an image in our head of what's going on. All right, now you guys will get this image on the exam if you need it. We have a sort of qualitative spectrum of strength. So up at the top here, we have our strong acids. So HCl is a strong acid. I'd expect 100% dissociation. Okay, acetic acid is a weak acid. It's coming down. I'm going down in my strength. I think when I looked at that, you know, let's say 1% dissociates. That number is going to change, but it's a small number. That's the point. It's a small number. I go down to NH4+. That's an even weaker acid. Okay, but it still dissociates a little bit, so maybe like 0.01% dissociates. And then I get all the way down to methane, so CH4. I put that into water, 0 CH4s give up a proton. It's not chemically stable for that to happen, so 0 dissociation. All right, we've got this spectrum now. Okay, and eventually we will quantify this, but for now in some of these questions, you'll be given this, so I need you to be able to interpret this diagram. All right, we have an inverse relationship between the strength of our acid and the strength of its conjugate base. Okay, so that's what the next slide shows, all right? If we look at, let's consider HCl first, okay? I'm gonna pull HCl. So HCl, we put it in water, 100% becomes H plus and Cl minus. This is a strong acid, meaning it really wants to give away its proton. Therefore, we can say Cl minus doesn't want it back, right? If HCl is always going to just keep giving away its proton, Cl minus, what we're saying is it doesn't want it back. In other words, Cl minus is a negligible base. It really doesn't behave as a base at all. Okay, on the other end of the spectrum down here, okay, if I were to put, let's use our methane as an example. If I put CH3 minus into water, That is incredibly unstable. That CH3 does a terrible job of stabilizing that minus. And so it's going to pull a proton off of water right away. Okay, it's going to grab a proton from water and become CH4 and OH minus. Okay, so this is an incredibly strong base. It's really unstable. It has to have a proton. So when it gets that proton, it is not likely to give away. So a strong base results in a negligible conjugate acid. Okay, and that happened, we go up on one side, we're going down in strength on the other. Up in strength and down in strength. All right, so let's look at this in action. All right. We're going to take an acid and a base and add it together in solution. And then we say, okay, what happens if those act as an acid and a base? What are our products? And now we can ask ourselves, which side are we going to favor? Okay? The take-home message from this is that the equilibrium will favor the side with the weaker base and the weaker acid. All right, so let's unpack that with an example. Okay? So I've put in SO4 2 minus, okay, and HCO3 minus. I'm going to start by identifying how do each of these behave in the reaction. Okay, HCO3 minus must have been, it's the only thing that has a proton. So that had to be an acid. It's going to give that proton away. So SO4 2 minus must have been the base. Okay, and I'm going to identify then my conjugate acid. It gains that proton and becomes an acid. HCO3 minus gives that proton away, and so now it's a conjugate base. So we will ask you, using this diagram, we'll ask you, are we going to have more reactants or more products? Okay, that's what the magnitude of K is asking. Are we going to have more products or more reactants? Okay, so that statement up there says the side that has the weaker base and the weaker acid, that's the side we're going to be on. So you pick something. Pick your acids. I'm going to take the acid, so I'm going to compare. For my left side, I'm going to pull the acid. HCO3 minus was my acid. On the right side, I'm comparing it with HSO4 minus, my conjugate acid. Okay, I want to know which one of those is stronger. And I go over to my diagram and I say, where is it? There's HSO4 minus, and there's HCO3 minus, all the way down there. Okay, so HSO4 minus is the stronger acid. Okay, HSO4 minus wants to give away that proton more than HCO3 minus. So I should find myself on the weaker side, which in this case was the reactants. So K will be less than 1. It favors the reactants in this case because it has my weaker acid. Necessarily, SO4 minus, 2 minus will also be my weaker base. Okay? So, see if that landed. So I'm going to give you an example to do, or a problem to work. All right? Try it with this one. So do that analysis. Who's acting as a base? Who's acting as an acid? You will then identify your conjugate base and your conjugate acid. Pick one. It doesn't matter if you're picking the acids or the bases to compare. Pick one of them. Whichever one is weaker, you're on that side. All right, where are we at? Thumbs up if you think you have the answer. Okay. So again, I start these processes by saying I want to identify acids and bases on my reactant side, and then I'll identify conjugate bases and acids on my product side. All right, so who lost the electron? Who donated it, right? That was H2S, right? Donated an H+. So H2S must have acted as my acid. Okay, NH3 was my base. Therefore, HS minus, that's my conjugate base. And this is now my conjugate acid. All right, so to figure out which side I'm more likely to be on, I now need to figure out which side has the weaker acid-base combination. Okay, so I'm going to pick, it doesn't matter if I pick the base or the acid, I'll do base this time. I'm going to compare the base strength of NH3 versus HS minus. Okay, so I got to go over to my base side, to the blue side, and I find NH3 down here, and then I find HS minus above it. That means that HS minus is weaker because we're going down in strength on the base side, and so HS minus is the weaker base, so therefore I should be on the product side, and that means that K is going to be greater than 1. Like a thumbs up, thumbs down. How does that process feel? Good. Yeah. Yes. Wherever the weaker is, yes. Because the weaker side, like think about it, if NH3 is the stronger base, then it really wants to accept a proton. So we should find it on the side where it has accepted that proton. And that's on the product side. All right. So that's like our qualitative. We will come back to this, and we are going to quantify this relationship on Tuesday, hopefully, if pacing goes as planned. All right, we're jumping into 16.3, the autoionization of water. We've already discussed this today, so hopefully this feels familiar. I'm calling water amphoteric. Okay, that's just a slightly broader definition of amphiprotic. Basically, it can act as an acid or a base, right? We could put it into a solution with acid and it's going to act as a base. If we put it into a solution with base, it will act as an acid. Okay, we're going to start by not thinking about it with other things, with HAs and Bs. I just want to think about pure water for the next slide. Okay. Knowing that water can act as both an acid and a base. All right? So if it can do that, then in theory, in my water, I should be doing this. My water molecules will be doing this. I could have one act as an acid and one act as a base on each other. This is called the autoionization of water, and that's going to produce some OH minus and H3O plus, even in pure water. My fun, weird fact is how I remember what autoionization means. I took an anthropology class that had some content on cannibals. If you are an auto-cannibal, you eat yourself. So when you say the autoionization of water, water is ionizing itself. And that's what I think about every time I see the word autoionization, and you also now will think of that, so you're welcome. Okay? You will never forget that auto means self, right? I mean, fun fact for the day. Good times. So, you guys are now experts, right, at writing equilibrium, right? We all feel good about it. So, if this is the autoionization reaction, I have one water molecule acting as a base, one acting as an acid, okay, and at room temperature, which is where we're mostly going to be functioning, 2 of every 10 to the 9th water molecules are ionized. So that's a really small percentage, but it's still important, all right? It's small, but it's there, right? So what is the equilibrium constant expression for this reaction. So I want you to write that down for yourselves. Big K, what does big K equal for that reaction? So big K. Am I going to include the H2Os in this expression? No, they're pure liquids. I'm not going to include them. W, we're going to give it a special name. We're going to run into a lot of special Ks moving forward. This is KW, and it's H3O plus concentration times OH minus. All right? And that turns out to be important. All right, so we're going to work with that for the next couple slides. At 25 degrees Celsius, we know that value. It's 1 times 10 to the negative 14th, okay? It's a really, really small number, right? So we have really small concentrations of H plus and OH minus in pure water, okay? So what I want you to get from this, what I really need you to take away from this, is that if you know the concentration of H plus, you can calculate OH minus, basically for any aqueous solution, provided that you have the K. There are some instances, and I'll talk about, I'm going to save that for Tuesday. I know the days of the week. There are some times when we change the temperature, and that changes the value of K. But if you know K, then you will be able to solve for H plus if you know OH minus and vice versa. Okay? This is how we are going to define neutral, acidic, and basic solutions. So I think those are familiar terms, but a neutral solution is when H plus concentration equals OH minus. Okay. Again, we can use this expression at this temperature with that number for any aqueous solution. So even if we put something else in there, like let's say HCl, and I make it really acidic, and I pump up my H plus concentration, that relationship still holds. Okay, even if H plus is greater than OH minus, H plus times OH minus is still 1 times 10 to the negative 14th. Okay, the same is true over here in a basic solution. Okay, now I have a lot more OH minus, but their product is still 1 times 10 to the negative 14th. Okay, this again assumes that number, the 10 to the negative 14th, that assumes at 25 degrees Celsius, because that's connected to the KW for 25 degrees Celsius. All right, so you now could get a question like this and answer it. So calculate the concentration of OH minus in a solution in which H plus is 2 times 10 to the negative 16th molar. Okay, I think I wrote this after I posted the slides, but that would be assumed. You can always assume room temperature, and on the exams we're usually pretty darn careful about including that. So I'd say OH minus equals 1 times 10 to the negative 14th divided by my H plus, which I have, so I plug that in, and you get that your OH minus concentration is 5 times 10 to the negative 9th. Okay? Make sure, punch that in for the next one, just make sure that you aren't making calculator punch errors, because this is a sort of a low-hanging fruit question. This is one of the very few equations you get on your exam sheet, that KW equals H plus times OH minus equals 1 times 10 to the negative 14th at 25 degrees Celsius. Okay. So I'm going to have an H plus concentration of 1 times 10 to the negative 14th And you see that this is a very small number, 10 to the minus 13. So in your head, you should be saying, okay, I should have a relatively large number for H plus. So I got 0.033 molar. Yes? Yeah. It's at that specific temperature. At room temperature. That's a constant, yes. That's just a constant at room temperature that we know. All right? So now we can interchange between H plus and OH minus. All right? It turns out, and I think this is familiar, that this concentration of H plus is really important, especially for a lot of biological systems. So much so that we need to talk about the H plus concentration quite a bit. All right? But it's like really annoying to say, like, you'd be like, oh, how much H plus is in there? Well, there's 1 times 10 to the negative 7th molar. It'd be nice to have an easier way to talk about it, which is where the pH scale comes in. All right, so instead of saying this mouthful, I'm going to take the negative log of that and say, hey, the pH of water, neutral water, is 7. And I got that because the pH is the negative log of the concentration of H plus. And so once you say the pH, what you're really communicating is what is the concentration of H plus ions, or H3O plus if we're being absolutely correct, but also the OH minus concentration, because they're inextricably connected. We know that from this. Okay? So pure water, pH equals negative log of that 1.0 times 10 to the negative 7th. Okay, I got 10 to the negative 7th because these two are equal, right? So what I did was I took the square root of this to solve out for H plus because those two were the same. And that's where we get a pH of 7 when those two are equal. That's what we call neutral. Okay, so you need to know that the pH equals the negative log of H plus. We'll talk about this on another slide, but a handy reminder that P, when you put the P in front of it, that means you're taking the negative log of whatever quantity is coming next. Okay, so pH, the negative log of H plus. Okay, so we wind up with a scale like this, all right? So we've got a lot of information here. Up in the top, we have increasing acid strength. So acid, we'll call it acidic solutions. They all have a pH less than 7. So therefore, their H plus concentration has to be greater than 10 to the minus 7th. Okay. This scale, and it's typical to show this scale goes down to 0, but there's no reason why we can't have a negative pH. That's just a really, really high concentration of H plus. Okay, and we just don't usually encounter it, but there's no reason why you can't have a negative pH. Same with our basic side. Okay, so down here where we are in a basic solution, okay, we have a pH greater than 7, which must mean that H plus is less than 10 to the minus 7th molar. All right? And then we have neutral in the middle here. Okay? Notice down here that this is all based on H plus times OH minus, those concentrations equaling 1 times 10 to the negative 14th. That tells me that this was made for room temperature, or the 25 degrees Celsius. Okay? And again, this is it is really useful to have the pH scale, especially because the range of plus concentration is enormous, right? At a pH of 0, we have 1 molar H plus concentration. Okay, that's pH equals 0. When we go all the way down to pH equals 14, we're looking at 1 times 10 to the negative 14th molar. Okay, so it's an enormous range. Okay, so using a log scale helps us see these on this a small number range rather than going from 1 all the way down to 1 times 10 to the negative 14th. Okay? All right, so now we should be able to do questions like this. What is the pH of a solution where H plus is equal to 2.5 times 10 to the negative 5th molar? And then we're going to ask you, is that acidic, neutral, or basic? Okay, so this is, I think, the easiest iteration of the question that I put together on this slide. pH equals the negative log of H plus, and I just provide that to you. And I was calculated when I punched this in, where is it, that it's 4.6. That's less than 7. This would be acidic, right? I could have gotten that it's acidic right off the bat looking at that H plus. That is a value greater than 10 to the minus 7th molar, so I know I must have had an acidic solution. All right, so do these two other examples here. Again, very likely that we give you a relatively straightforward question. This next one's a little bit harder because you have to go from OH minus to H plus and then calculate pH. There is another route, and we'll look at the other route in the next slide. All right, so I look at this and say, I've got OH minus, they're asking me for pH, so I'm going to convert and get my H plus concentration. Okay. I notice that this is a relatively, again, this is small concentrations, but it's a big concentration relatively, so I have a lot of OH minus, which means that I'm going to have a basic solution because I'm not going to have very much H plus. Okay. So this was 5 times 10 to the negative 12th molar. Then I take the negative log of that value. And I got 11.3. That's greater than 7, so we call that basic. All right, the other direction that we could go is say, hey, here's a pH. What's my concentration of H plus? You could then extend that, say, what's that concentration of OH minus? Okay, so we want to remember now that we'll say, and this is right off the bat, we see that that's greater than 7, so I'll call this basic. pH equals the negative log of H plus equals 8.4. I'm trying to isolate that. So I'm going to move my negative sign over, and to get rid of the log, I'm going to raise both sides by 10. Okay, so remember that log is a base 10 system. Natural log is a base E system, so in the same way we got rid of ln's by raising to, like with E, we're going to do that for logs with 10s, all right? So I've got H plus equals 10 to the negative 8.4, and that's 4 times 10 to the negative 9th. Yes? Because I have it's the negative log, so I move the negative over and then take both sides by 10. Okay.
For the second question, could you also just put the 2 times 10 to the negative 3 into a negative log and subtract usually 14 minus?
Yes. Great segue.
Okay.
All right. The other P scales. You read my mind. All right, so we can also use POH. All right, so POH means the negative log of the OH minus concentration. All right, so we can easily calculate that. If we were to extend this out and take the negative log of KW, okay, so we know, let's expand this out. We're going to do this real quick, okay, so PKW, the negative log, and we know that at room temperature, this is 1 times 10 to the negative 14th. So this equals 14, okay? The other definition of KW that we know is it's the product of OH minus times H plus. So I could write out the negative log of OH minus times H plus, right? And then I can expand this and say, well, I know that the log of A times B equals the log of A plus the log of B. So I'm going to use that to my advantage here and write out that the 14 equals the negative log of OH minus plus the negative log of H plus. In other words, now I can recognize these two as something more significant. 14 equals POH plus pH. So I also have this relationship to work with. So when we go back into that problem before, instead of finding H plus concentration and going from there, I can just find the POH and plug that into my relationship with pH, right? So that would be another route using that relationship. Okay, again, we are functioning, as soon as you see that number, we're saying we're at 25 degrees Celsius. All right? So here's our basic calculations. And now we move into some of the chemistry. All right, so we're going to start with the easier acids and bases. And those are our strong acids and bases. Okay? So again, these are the things that completely dissociate, which means we don't have to deal with equilibrium because we just know that they 100% react. And so the concept of equilibrium doesn't really do much for us because it's not a balance. It's just all of it is dissociating. All right? So on the next slide, change this. I wanted to write out my 6 strong monoprotic acids. Okay? Monoprotic meaning it has one proton that it is very likely to give away, that will 100% of the time give away. Okay? You need to know these. In theory, you remember them from your last chemistry class. Okay? HCl, HBr, HI, HNO3, HClO3, and HClO4. Must know these. When you see one of those 6, you say they 100% dissociate. Therefore, the molarity of any strong acid, which we'll say we'll be specific, strong monoprotic acid is the molarity of H plus. Right? So if we had 1 molar of HCl, that means I have 1 molar of H plus and 1 molar of Cl minus. For pH, that's what I'm really interested in. So it's directly related, 1 to 1. It goes in, it completely dissociates. I have that much H plus. This is not going to be the case when we look at weak acids, when it doesn't 100% dissociate, and that's what we need to use our knowledge from chapter 15. Okay? So those are the strong acids I need you to know. I'm just seeing some heads going up and down, getting those written down. All right? So know those. Love them. Write them on a card and put them under your pillow. All right? The strong bases that I need you to be aware of, all right? They're usually ionic hydroxides of metals. Okay, so we're looking at NaOH. Okay, what else did I? Lithium hydroxide, potassium hydroxide. All of these generate OH minus in a 1-to-1 ratio, right? I put in 1 mole of NaOH, I get 1 mole of OH minus. That is now my OH minus concentration I could use to calculate pH. Okay, the other set that you might encounter are from group 2. So I could have calcium hydroxide, right? Or magnesium. I also have barium on here. Okay, notice that these will generate 2 OH minuses. So if I put in 1 mole of calcium hydroxide and all of it dissolves, I'm going to have 2 moles of OH minus. Okay, so just watch out for the ratio when you do that math. These are pretty straightforward. You see the OH minus in there. I have two like sneaky bases, two sneaky strong bases that I want you to know. Okay. So one of them, okay, is the oxide ion, and the other is the hydride. So if I were to put sodium oxide, so here's sodium oxide. If I put that into water and it dissolves, I'm going to get 2 Na plus and O2 minus. Okay? Really, really strong base. That single oxygen is not very good at stabilizing 2 whole extra electrons. Okay? We're putting too much negative charge into a small space. It will immediately take, okay, O2 minus, will immediately react with water, and it'll pull one of those protons off. And here's the tricky, the careful part. When it pulls that off, but it will leave an OH minus. So an oxide, 1 mole of an oxide will make 2 moles of OH minus. Okay? So you just have to be aware of that doubling, because what it leaves behind is also OH minus. And we are now in the business of being very interested of knowing what OH minus concentration is. Okay? So I'm going to make 2 there. Okay? So oxides make double the OH minus. Okay? And then the other one is a hydride. So sodium hydride. Okay? This is one of the very rare odd cases where we are putting hydrogen with something more electropositive. And so hydrogen has the extra electron. Also not very stable. It's very small. We're putting too much negative charge into a small place. Doesn't like that. Okay, so it will immediately grab a proton as well. That's a really strong base. Okay, so it's going to use its 2 electrons, grab an H, it makes H2 gas that evolves off, and we're left with 1 OH minus. So you just need to see NaH, sodium hydride, see that as a base, and that's a 1-to-1. Every unit of NaH is going to make 1 unit of OH minus. Okay? So those are the other 2 bases that I want you aware of, the oxide and the hydride. Okay. All right, so let's do some practice problems. All right. What is the pH of a 0.15 molar solution of HNO3? You look at that, you say HNO3 is a strong acid. That is telling me the H plus concentration. So this is also the H plus concentration because that 100% dissociates. Okay, so my pH will be the negative log of 0.15, and that's 0.82. It's really acidic. Okay, so now I want you to calculate the pH of this 0.0005 molar barium hydroxide solution. Really acidic, because it's way less than 7. Okay. Key here, we are dealing with a base that will generate, when it dissolves, 2 OH minuses. This concentration is for that whole salt. So my concentration of OH minus in solution will be 2 times this value. So I'm going to have an OH minus concentration of 0.001 molar. Okay, I'm going to do it the other way here. I'm going to find the POH first. I'm going to take the negative log of that value. That's my POH. That is a 3, but I'm asked for pH. Okay, remember that pH plus POH equals 14. So pH equals 14 minus 3. So it's 11, and it's basic. Okay, so these are questions that I see every semester students get wrong because they don't finish their analysis, and they don't stop and think about it. You just put in something with a bunch of OH minus. If you stopped at the POH and you put in 3, and you're like, oh, it's acidic, you should, like, sirens should be going off in your head because you're like, no, I added a bunch of OH minus. This needs to be basic. Okay, so just make sure you finish the analysis. Say, this is basic, all right? And the last thing, what is the concentration of an HCl solution with a pH of negative 1.2? Okay, so I promise we can do negative pHs, and we're going the other direction here. Okay, I know, since this is a strong acid, that whatever the concentration of H plus is, that's my concentration of HCl. Okay, so I can solve for the H plus concentration with this information. So pH equals the negative log of H plus. That equals negative 1.2. So H plus equals 10 to the 1.2, and this is a scarily concentrated HCl solution at 15.8 molar. Okay? Good? Good-ish? How is this familiar content? Give me if you've seen this before. Okay. All right. We have lots of practice on this tomorrow in recitation. I am sorry, not sorry, but I'm going to use my last 6 minutes to just talk about weak acids, all right? Because this is now where all of the concepts come together, okay? So lock in, give me your attention for 5 minutes, all right? Okay. We just named 6 strong acids. There's a lot of acids out in the world. Most of them are not strong. Most of them are weak, and so they only partially dissociate, right? So we have to deal with equilibrium, okay? Now we're using our equilibrium arrows here, right? Okay, we didn't need to think about that for strong acids because it was just a 100%. Doesn't matter, it's all products, okay? Now it matters, all right? So again, we drew this visual earlier, but now we are wondering, what is this balance, right? How much dissociates? Because if we want to know the pH, which we've said is a very important quality of a solution, we need to know the concentration of H+. And that's going to be related to how much of our HA dissociates, okay? If a lot dissociates, then it's a very acidic solution. If a little bit does, then it's less acidic, okay? So we're going to start out by writing the acid dissociation constant. Again, this is big K, and we just make it special by putting a subscript A next to it because it's for acids. All right, so Ka equals H plus, because I'm being lazy and I'm dropping my H2O in this equation, which is standard. But remember that that is really what it is, and that's the hydronium ion. Okay, water drops out. It's a pure liquid. This is our acid dissociation constant. This is what we're going to work with for a lot of the next couple weeks. This and Kb, which is the weak base dissociation constant. All right? So what do we say from this? If Ka is big, right? More products. And I'm going to put big in quotes because it's never going to be that big. More products, okay? Which would mean a more acidic solution, right? So let me introduce you to some of our more common weak acids that we're going to encounter, all right? So of course, this is probably very overwhelming, but here's like a big list of some of the weak acids that we deal with. What I want to point out to you is the value of Ka. Notice that Ka for all of these acids is less than 1, and it ranges from 10 to the minus 2 down to 10 to the minus 10th. These are small numbers. If we ask you to calculate a Ka value and you get something like 10 to the 10th, you should stop yourself and say, that's wrong. It should be a small number, right? Not very much of these weak acids dissociate. So we should be getting small numbers. Okay, let's make a comparison between two of them. We're taking nitrous and hydrocyanic. Onto the next slide. Oh, I lied. We take chlorous acid, all right? Notice, both of these are small numbers, okay? They're really quite small. We can write in what these equal. We would look at this and say, we are going to have, they are both weak acids, but I am going to qualify HClO2 as the stronger weak acid. And HCN is our weaker weak acid. Okay? So again, in both cases, we have very small Kas. So reactants are favored. Most of this doesn't dissociate. Okay? But because HClO2 has the larger Ka, it is a stronger, weaker acid. In other words, if I had the same concentration of these two acids, HClO2 is going to have the higher concentration of H+ and be more acidic. Okay? All right. We're going to end there, but I have a couple announcements I want to make really quick. Okay? I got 1 minute. All right. Practice exams are up. All right? You have an exam a week from tomorrow. If you want to take those practice exams this weekend, we still have content to cover on Tuesday. I have posted old lectures so you can get ahead if you want to. I do not recommend taking the practice exams without